Welcome to Ready to Derive. In this video, we build on the work from the previous video I made about rate of change and make the important move from finding the instantaneous rate of change at one particular value of x to generating a formula to find this quantity at any point on a function. In so doing, we formalize the definition of the derivative, one of the most important concepts of calculus. I hope you are feeling totally ready to derive today, as that's just about all we will be doing throughout this video. Enjoy. So let's begin with a recap from my previous video on rate of change. In particular, this context of the ball being thrown up in the air with this initial velocity of 60 feet per second, and this function which models its height after x seconds. And if you recall, this was the graph of the motion. So the question that we asked in that video, what is the velocity of the ball at 1 second, which translated to what is the slope of the tangent line at 1 second, we were able to derive a formula for the instantaneous rate of change. And we realized that, well, if we want the velocity at 1 second, we would work out the average rate of change from 1 second to 1 plus h, just a little bit. And we calculate that out, plug those into the function f of x above, do a lot of algebra, and we would get the desired answer. But then what if we wanted it at 2 seconds, i.e. the slope of the tangent line at 2 seconds? Well, we'd have to take away the 1 and put in 2 and do all the work all over again. And if we wanted at 3 seconds, which would be the slope of this tangent line, once again, we'd have to put in 3 here and do all the calculations again to get that particular instantaneous rate of change. So we finished by saying there must be a better way. Surely, instead of doing this over and over again, perhaps we could just keep it general. Instead of committing to a particular number, what about if we just work this out at a general value of x? So let's find this formula for the instantaneous velocity of the ball. We'll recall the instantaneous rate of change formula. This time we have replaced, formally what we had here was we would use a number like a in both here, and now we're just going to stick with x and keep it general. So our first step, I'm going to use some color coding here to help us. Our first step is to find f of x plus h, which means replacing x plus h anywhere you see an x in this formula. So 60, replace x with x plus h, and x squared. And I'm going to put brackets around here to kind of keep us organized. And then we're going to subtract from that the function f of x. Again, so if I put that without bracket, that wouldn't be accurate. So I'm going to put the brackets there to help us. And now we're going to distribute and FOIL and really try to combine like terms and simplify. So first of all, it's convenient to just expand x plus h squared, which if you FOIL out would make this. And now we can distribute away. So we have 60x plus 60h minus, and now I'm going to go straight and distribute 16 into there. 16x squared minus 32 xh minus 16h squared. And I have that minus, and once I open up the brackets, it becomes 60x plus 16x squared. Now notice at this stage we have some canceling going on. That 60x cancels with that, negative 16x squared with plus 16x squared. And we get to a situation where, let's see, I'll move to white now. So this is our simplified expression. And you might wonder, well, why haven't we even tried to plug h equals 0 in? But I hope you notice that if you plug that into the numerator and the denominator, you'd get 0 over 0, which is indeterminate, which means we have one more step to do. Conveniently, h factors out of the numerator, and we are left with this expression. And since h factors out, and is on the top and the bottom, we can cancel that. And we've arrived at a place where we can actually plug in h equals 0. We can find this limit. So we get 60 minus 32x minus 16 times 0. And we have actually then derived that the instantaneous rate of change for the motion of this particular ball is 60 minus 32x. So in the next slide, we'll see how that makes all our calculations that much easier. So let's recall the equation of the height of the ball anytime x and the graph of its motion. And in the previous slide, we derived the formula for the instantaneous velocity of the ball, which is 60 minus 32x. So we can actually use that now at various times to work out the velocity of the ball. In the previous video, we really took a lot of work every time we wanted to recalculate the velocity at a particular value. So at time equals 0, it would be 60 minus 32 times 0, which is just 60. And at time 1, let's just fill these in. It would be 28. That should be familiar from the previous video. 60 minus 32 times 2 is negative 4. And 60 minus 32 times 3 comes out to be negative 36. We're going to stop and revisit 4 in a moment. And if we think about these, so what do these values represent? Well, at time equals 0, the instantaneous velocity is 60. That would be the slope of the tangent line right there. At 1, the instantaneous velocity is 28 feet per second. That would be that slope of that tangent line. T equals 2, negative 4. T equals 3, a little steeper, definitely negative 36. But there's no point plugging in T equals 4 because the ball's already hit the ground. But the one thing that we could establish is that we have 60 when the ball leaves the ground and with an initial velocity of 60, it returns with the same, but in a negative sense, negative 60 feet per second. So this formula is very powerful, very versatile, and can be used at any value of x. Just want to point out a couple of things. If we look at the 60 here, if we go back to the original problem, that was the initial velocity of the ball was a 60. And you see that 60 right here. And if you look now at the pattern in the table, well, even the formula is saying, look, we just take negative 32, that's just dropping by 32 every time. That negative 32 should ring a bell. So the initial velocity of 60, that actually appears in the formula, and the negative 32 is the acceleration due to gravity. So negative 32 makes up the formula for velocity. Acceleration due to gravity is negative 32 feet per second squared, which really means that the velocity starts off at 60 feet per second, and then every second drops by an extra 32 feet per second. So down another 32 feet per second. So this formula here, 60 minus 32x, is actually, if I change the initial velocity to 40, it would be 40 minus 32x. Later in the course, we'll learn that actually, if we just start with the velocity formula, we can actually derive the formula for the motion of the object. So some powerful stuff here. So now I have the pleasure of introducing you to the derivative function. And in order to do this, I'm going to call up the velocity time information from before and the graph. I've changed the scale on the graph to allow me to plot the velocity values. So if we recall at time is 0, we found that the velocity was 60. At time equals 1, we found that the velocity was 28. So I'm going to just plot that here. 28 looks like it's about this. I'm using the y-axis to represent velocity simultaneously for the blue graph, even though it represents height for the red graph. At 2, it was negative 4. And at 3, we found it was negative 36. And we could fill in many other points because we have the equation for this motion, but I hope you can see that the velocities seem to lie along a linear function. So I'm going to put that line and connect the points, and then think about how intimately these two graphs are connected. So the red graph is f of x equals 60x minus 16x squared, and we worked out the instantaneous rate of change in the previous slide, and we get dy by dx equals 60 minus 32x, and there we see it. 60 is the y-intercept, and minus 32 is the slope of that. So for every 1 second, the velocity drops by 32. Well, this is a function in itself. I mean, we all know that linear functions are functions in their own right. So we're actually going to introduce some new notation. And it's this notation, which represents, now we're going to talk about this being the derivative of f of x. It reads f prime of x. And the reason that we want to call it f prime is just, well, we could call it g of x, but then we don't understand how intimately it is tied to f of x. So in the same way, when you talk about the inverse of a function, you say f and its inverse would be f minus 1. You could call its inverse g, but why do that? Because it could get confusing. In that same way, when we have a function f of x and we want to talk about the derivative of it, we label it f prime x. So dy by dx will still be using that, but f prime x we'll be using whenever dealing with function notation. So once again, that's the derivative of f of x, and this is one of the most powerful concepts in calculus, as I've said, as you will see moving forward. So let's pause here to give a formal definition of the derivative. The derivative of f of x is defined to be another function, which we call f prime x, which is equal to this limit. And if we just take a look at what this means again, just to give it context, we are talking about, if we, let's see, call this, instead of calling this a, we will call this x to keep it general. And when we talk about the derivative, we are talking about the slope of the tangent line again, or the instantaneous rate of change at any point on f of x. And remember that f prime x is a function in itself. Once we derive it, we could graph it in the same way that we could graph f of x. So let's practice using the derivative formula to find the derivative of this cubic function. So the first thing we need is f of x plus h. Remember, that means replacing x with x plus h in this function. So x plus h cubed plus 5. We're going to put brackets around there just to be safe. And we're going to subtract out f of x, which is just this. And in the next step, I'm going to just release the brackets. I'm not going to take care of x plus h cubed just yet. I'm going to release the brackets, and remember that the whole point of having the brackets is so we don't forget to distribute here. And notice that we can simplify a little here. The 5's cancel. Notice also that the 2 is a common factor of the numerator. So I'm going to extract that out, which is permissible. It's a limit law. And in the next step, now we're going to take care of x plus h cubed. So I'm not going to do it completely for you here. I'll leave that up to you, but you would have to take x plus h and multiply it by itself 3 times. You would have to multiply the first 2 to get a trinomial, and take that trinomial and multiply it by the remaining binomial. And you will get, if you do that, you should get this expression. There's a lot of symmetry going on here. And for those of you who are familiar with the binomial expansion, you'll notice that 1, 3, 3, 1 are the binomial coefficients, and also one of the third row of Pascal's triangle. So if we put this, let's bring this over here, plus 3x squared, h plus 3x h squared plus h cubed, that's just x plus h cubed. We mustn't forget, we've still got a minus x cubed here. Conveniently, the x cubes cancel, and that's kind of important because they don't have a factor of h in them, which will make sense when we get to the next step. So the remaining terms all have a factor of h in them. So that means Well, let me just write those out first. Let me just write them so it's not so cluttered. Since they all have a factor of h, and you might say, oh, could we plug h equal, why not plug h equals 0 in right now? But you'll see that the numerator would go to 0, the denominator would go to 0, and that would be indeterminate. So we have to somehow get h out of the picture. The h in the denominator is a problem, so let's just factor out. So 3xh plus h squared. And then we see the h's cancel, and we get to a stage where we can actually plug in h equals 0. Now don't forget we have the 2 on the outside, and so we have the 3x squared, that doesn't have an h, but we notice that this will go to 0, this will go to 0, and we are just left with 6x squared. So we have just derived the derivative of 2x cubed plus 5. So there we are. In this slide, we're going to practice finding the derivative of a square root function. So as always, we start by finding f of x plus h, which means replacing x in the function with x plus h. So we're going to have 3 times the square root of x plus h minus 2. Don't forget brackets. And from that, we're going to subtract the original function like that. Okay, and the next step is to release the brackets. The bracket wasn't really necessary in the first bracket, but the second bracket is of course important because you must distribute that negative. And then we see that the minus 2 and the plus 2 cancel. And once again, we seem to have a common factor of 3 in the numerator, so I'm going to pull that out for the next step. So what we're left with is square root of x plus h minus the square root of x. And you should recognize that we practice finding limits involving radicals in the first unit, and we realize that the only way to achieve this, remember, if you plug in h equals 0 at this moment, you would get 0 over 0, indeterminate, so we have to do some algebraic manipulation, and that's multiplying by the conjugate of the radical expression to the top and the bottom. Now, the bottom, the denominator, you don't want to distribute. You need to keep that h factored out. But the numerator, we definitely want to multiply that out. And if you multiply the first terms, you'd get x plus h. If you notice, because of the minus and the plus, the outer and inner terms will cancel. And then multiplying the last terms, we'll get x. And conveniently, the x's cancel. And we are left with just h on top. Well, and once again, that the whole point was that h equals 0 was illegal to plug in because at this point we still get 0 over 0. But if we notice that they cancel out, at this stage we get to a point where we could plug in h equals 0, right? We can plug it into what's remaining, and we get 3 times 1 over square root of x plus square root of x, which is 3 over 2 square root of x. And we have derived the derivative once again. So let's end with one more example, finding the derivative of a reciprocal function. And as always, we'll begin with f of x plus h. We're going to have to replace x with x plus h. So we're going to get something a little cumbersome here, but don't worry, bear with me. We'll simplify the situation. So x is replaced with x plus h, but don't forget there's a plus 2 there. And then we're going to subtract out from that f of x itself, which is 1 over x plus 2. Now at this point, once again, if you try to plug in h equals 0, you'd get 0 over 0 indeterminate, so we have to practice what we learned in the unit on limits and simplify this fraction. Right now it's a complex fraction. We want to reduce it to a single simple fraction. And the way we could get common denominator on the top and then do keep change flip, there's a lot of, it's a bit cumbersome. So instead we're going to multiply the top and bottom by the common denominator. So, and we'll see what effect this has. So again, with the denominator, best Don't distribute. It will become very messy. You want it factored out so that things will eventually cancel out. And on the numerator, you'll be left with, so if you sort of think about this carefully, if you take this whole expression and multiply it to the first term, the x plus h plus 2 will cancel out, and you'll be left with just x plus 2. And don't get the minus. And if you distribute it now to the second term, the x plus 2 factors will cancel out, and you'll be left with x plus h plus 2. But don't forget to put parentheses there, just to be careful. And then if we simplify the numerator, I hope you can see that the x will cancel with, that will become x minus x. The 2 will cancel with this 2 here because that 2 is really a minus because of this outside here. And then all we are left with is negative h. Once again, the h's cancel. Probably should write that we're left with negative 1 on top. And so we are at a stage where we can just plug in h equals 0 legally. So we're going to put that to 0. And we end up with negative 1 over x plus 2 squared. So we have found the derivative of the reciprocal function, and our mission is completed. And that brings us to the end of this lesson. I hope you found it helpful, and if you did, please do click like and/or subscribe to my YouTube channel, Ready to Derive. Thank you.